And then all this on the church, okay, we have this stained glass. It also comes from transition element ions, okay? Yep. And then you know that for nuclear energy, right, everybody? For nuclear energy, okay, you know that we have uranium as the feedstock, and then we have oxygen and steel as the starting materials. But that's one important thing that a lot of people don't know, right, is the radioactive waste. Okay, so a lot of people are campaigning against the use of nuclear energy. Why is that so? Because for nuclear waste, right, okay, after all this uranium, oxygen and steel are used up, okay, the radioactive waste actually comprises various isotopes of almost all the transition elements in the periodic table. So all these isotopes, right, some of them are radioactive. So you can imagine how toxic the nuclear waste is. And then I'd like to let all of you see an article, right? If you look at this article, like in December 2007, right? Okay? So our PM says that nuclear power is not for Singapore because too dangerous and we are too land scarce already. Okay, but 3 years later, okay, if you look at the Straits Times, 3 years later, 2010. No, now we are preparing for a nuclear power option because I think energy is getting very scarce. So even if we are land scarce, we will still need to consider this. But of course, it needs to take many, many years of preparation and educating of the people. Okay, so, well, everything is an option. So do use your energy wisely. And then last thing before I move to the lecture proper. Okay, I believe all of you, right, you have seen all this before, right? X-Men, Wolverine, and then we have Iron Man, and we have Captain America. Okay, what is the common thing about all these three superheroes? Okay, I heard handsome. Not because they are very handsome, but because all they are, okay, you know this Wolverine, right? This metal is actually already infused with the skeleton already. So Wolverine, right, actually he's very strong, okay? And then Captain America, this shield, he can always throw everywhere but it won't break, right? Okay, and then Iron Man, this armor is super strong also, and they are made of this adamantium. Okay, but of course this adamantium, if you try and go and look at your periodic table, you will never find it because it is a fiction, it's a fictitious alloy. So this alloy, right, actually contains the transition element iron together with some other steel alloys, okay? By the way, Marvel Comics, right, they like to use this adamantium to make a lot of its weapons. Okay, just something. So in this case, right, yeah, let's move on to the transition elements lecture proper. Okay, yeah. So let's take a look. For transition elements, right, okay, let's take a look at the first part, D block elements. Okay, D block elements, right, I'd like you to take a look at the table. This whole stretch, right, is the D block elements, the one in blue color, but for A-level syllabus, we are only concerned with the first row of D block elements, okay? So this is from scandium to zinc, but later you will see that scandium and zinc, they are not transition elements, they are just called D block, okay? So I would like to do a quick recap of your electronic configuration. How do we write, right? If you recall the Aufbau rule, okay, we will always fill in the 4S subshell first, followed by the 3D subshell, okay? So why is that so? If you take a look at this diagram, you will notice that the 4s orbital is actually lower in energy than the 3d orbital. So we always fill in from lower energy level. So we will fill in 4s first, followed by 3d. Okay? And then always remember, when we fill in the electrons, we fill in the 4s orbital first. When we take out the electrons, ionization, we also remove the 4s electrons first. Okay? So if you take a look at the next page, right, we see this table. So in this case, right, not all D block elements are transition elements. Instead, out of all these that you see here, right, from titanium to copper, these are our transition elements. Okay, so you notice scandium and zinc, they are not included. So you can generally say that in a whole subset of D block elements, right? So in a whole D block elements, only transition element is a subset of it. Okay, so take note. So how do we define transition element? Later we will go more into detail, but this is just an overview. Only D block elements that can form ions with partially filled D subshell are transition elements. In your lecture notes, right, can you just write in the D subshell? The D is missing. The partially D subshell, okay, are transition element. Okay, can? And then after that, right, chromium and copper are unusual in that the 4s orbital is not fully filled. So if you look at this, right, the 4s orbital only has one electron each. Okay? So if you take a look, right, if you write the general electronic configuration, okay, you will have your argon. Argon as your noble gas core configuration. Okay? So in this case, every one of it has argon, and then you have 3dx and 4sy. So only copper and chromium has 4s1, simply because they want to fulfill the half-filled d orbital. So 3d5 and 3d10. If you remember what we went through last year, right? You remember the U are special, remember? U are special, so copper and chromium are special in this case. So why do they prefer to have a half-filled D subshell? Okay, this one, right, is simply because if it is half-filled, the 3D orbitals, right, the electron cloud will be more symmetrical, and this one screens the nucleus more effectively, so it's favorable. So you just need to know, okay? So next part, we are moving on to the next page already. Okay, how do you determine the electronic configuration of a transition metal cation? So in this case, if you look at checkpoint 1, there is this box, right? Okay, when D block elements, they form ions, right? 4s electrons are lost first. Remember, we put in the 4s first, we also take out from 4s. Okay, so why is that so? Okay, when the 3D subshell is occupied by the electrons, okay, so this energy level diagram that you see here, right, the 4s electrons will be repelled further from the nucleus, so it will move up a little bit. So when it moves up, right, we know that we remove from the higher energy level first. Okay, so repel up to a higher energy level. So now the outermost electrons becomes the 4s subshell electrons. So we remove from the 4s first. Okay? So let's take a look quickly at checkpoint 1. So they are asking you for the electronic configuration of the ions titanium and iron. So this part, right, there is important thing to take note is actually to write the electronic configuration of the atom first. So in this case, right, for titanium we have 22, for iron we have 26. So very quickly, right, you can actually know that argon is 18 electrons. Okay, argon is 18. So we have, for titanium, we have 4 electrons left. We must fill in the 4s2 first, followed by the 3d2. For iron, right, 26 electrons minus 18, left 6. Left 8. So I must fill in 4s2 first, followed by 3d6. So for ion with titanium plus, how many electrons do we remove? 1. If I remove 1, I remove from the 4s first. So you should actually get 3d2, 4s1. So very simple. For titanium 3 plus, of course, remove 3 electrons. So again, remove from the 4s first. So you should get 3d1 left over. This one is easy, right? Can Okay, one common mistake, actually some of you here will still make this mistake. What is this mistake? Very simple. When you are supposed to write electronic configuration, some of you will do this. 22, right? So if I have titanium plus, what I will do is I will take 22 minus 1 equals to 20. Then you will start to write argon. What is the mistake? Sorry? Oh, sorry, 21. Okay, so this is the major mistake. Okay, so 21. So this is 18, then after that followed by 3, left 3 more. Common mistake is you will fill in 4s2, then you get 3d1. So this is the mistake that some of you will still continue to make. Okay, so please take note, you have to write out the atom configuration first, then take away the 4s. Okay, not minus away 1, then you write a new one from there. Okay, can? So let's take a look at iron. Okay, so for iron, right, I have 26 electrons, I remove 2. Again, I must remove from the 4s first. So I'll be left with 3d6. Okay, always remember to write the atom first. Then for Fe3+, you remove 3 electrons, so you're left with 3d5. Okay, Ken? Let's move on to checkpoint 2. Okay, checkpoint 2, right, the question asks for which of the following ions contains 5 unpaired d electrons. In this case, same thing, because if you notice, all the options are ions. So you have to write out the atom electronic configuration first. So for chromium, okay, you have 3d5, 4s1. Please take note, chromium, you are special. So chromium is a special one with 4s1, with a half-filled 3d5. Okay, then if you remove 3 electrons, you will be left with 3d3. Okay, if you look at option C, manganese. Iron. Iron 26 electrons, you write the atom first, you should get 3d6, 4s2. Remember, fill in the 4s2 first. After that, remove 3 electrons, you should get 3d5. Similarly for manganese, remove 3 electrons, you get 3d4. And nickel 2+, you remove 2 electrons, you're left with 3d8. So if they want 5 unpaired electrons, you can actually draw out the electron in box diagram. 1, 2, 3, 4, 5. So of course, if you have 5 electrons, you will have 5 unpaired. Answer should be B. Okay, this one is very easy, just a recap. Can we move on to next page already? Can? Move on to the next page. Alright, next part, right, we are moving into the actual information about transition elements. So this part, the definition, everybody please take note. It is a D block element. Remember, transition element is just a subset of D block element. So transition element can form at least one stable ion. It must be an ion with a partially filled D subshell, because D block element. Okay? So in this case, right, based on the above definition, scandium and zinc, they are not transition elements, although they are in the same first row. Simply because when scandium forms an ion, it only forms scandium 3+. This is the only oxidation state that scandium will exhibit. So if you notice, right, if you write out the electronic configuration, scandium 3+, it has 0 D subshell electrons. So it is not a transition element based on this. Similarly for zinc, it only forms Zn2+. It is the only stable oxidation state. Similarly, when you remove 2 electrons to form Zn2+, it has 3d10 left over. So 3d10 is a full subshell. It is not partially filled. So by definition, it is not a transition element. Okay. Moreover, right, if you take a look at the box below, the solutions of zinc and scandium, they are colorless. Okay, transition elements, they are usually colored. Okay, and then zinc and scandium, they also show no catalytic activity. Generally, your transition elements are catalysts. Okay, let's move on to checkpoint 3. Okay, checkpoint 3, right, let's take a look. This part, they talk about the element copper forms Cu plus ion. Okay, if you write out the electronic configuration, it will have 3d10. So 3d10 is actually a fully filled D subshell. So in that case, is copper still a transition element? It is, right? Why? Because now we are only talking about Cu plus. If you write Cu2 plus, you remove 2 electrons, so you remove the 4s1 and you remove 1 from 3d10, you are left with 3d9. 3d9 is partially filled. Okay, so it is at least one stable ion, which is Cu2+. So it is still considered as a transition element. Can everybody? So far is mainly atomic structure, very easy. Let's take a look at the physical properties. Okay, for physical properties, right? Okay, you will need to know it well, because next time you can be the makers of the Iron Man suit, maybe the new generation one. Okay. Anyway, they have high melting and boiling point. That's why Iron Man can fly up all the way into space without melting. Okay. And then he have good electrical conductivity, but luckily he doesn't get electrocuted because maybe he has some other things with him. Okay. Then he have high density, very heavy. Okay. And similar. Okay, this one not related. Similar atomic and ionic radius, and transition elements, they also have similar first and second IE. Okay, so let's take a look at the next page, the graph. Okay, for melting and boiling point, right? If you take a look at the gray box, okay, for this part, right, you will need to know how to explain why the atomic radius, the ionic radius, are relatively constant. Okay, and also be able to describe all these physical properties. Okay, so for transition elements, usually they have high melting points and usually above 1000 degrees Celsius, except for zinc. If you notice here, right, zinc usually is quite low. Okay, and then compared to the S block elements, right, is all your group 1 and group 2. Okay, so melting point of the transition elements is definitely higher. Okay. So if you notice that there is a dip over here, can you notice this part? Can you please circle or highlight? Manganese, right? You notice it is like an anomaly. The melting point and boiling point are lower than usual. So why is that so? Okay, I mean this part is just intermediate minima. Okay, it's just a term to say that this is like a lowest point. I mean as a dip. So one possible reason to explain this is that there is a half-filled subshell of 3d electrons. Okay, this configuration is particularly stable, so the electrons are not readily available for metallic bonding. So the melting point and boiling point are lower than usual. Okay, so if you notice, this part is the electronic configuration, 3d5, half-filled. Okay, now I'd like to move on to comparison. Okay, this comparison is between titanium and calcium. This part you can actually write down quickly. Calcium is our S block metal, group 2. Okay, besides knowing the physical properties of transition elements, you also need to know how to compare with S block elements. So in this case, right, you remember your SBE. So both are metals, giant metallic structure, but titanium has a higher melting point because of a stronger metallic bonding. So if you recall from your chem bonding, okay, our mobile and delocalized electrons, okay, in this case, the more you have, the stronger the metallic bonding, right? So if you take a look at the electronic configuration, okay, I suggest you quickly take this down. For titanium and calcium, you can just jot down the electronic configuration quickly. Okay, so for titanium, the 4s and 3d electrons, all of them are available for delocalization into the sea of delocalized electrons surrounding the metal cations. So altogether 4 electrons. Whereas for calcium, it can only delocalize 2 electrons. So 4 versus 2, of course, 4 will contribute to a greater metallic bonding. Okay? Another reason, if you give away 4 electrons, then you will have a greater positive charge, right? So titanium actually has a larger cationic charge. Okay, and because titanium has a higher nuclear charge, and hence effective nuclear charge, right? You have a smaller cationic radius. Okay, this is a recap of chem bonding also. The second point will be charge density. Remember, if you explain the melting point or boiling point of metals, another explanation is the charge density. So charge density will be proportional to charge. over ionic radius. So if you do a quick mathematical manipulation, larger charge and smaller ionic radius, your charge density will increase and it will also contribute to your higher melting point and boiling point. So quite easy, right? Okay, next part, right, is on electrical conductivity. So electrical conductivity generally increases from scandium to copper. This is very simple because as you go from scandium to copper, there is a greater number of mobile and delocalized electrons in the giant metallic structure. Okay, the more electrons you have in the sea of delocalized electrons, the higher your electrical conductivity. And generally, copper and silver, they are the best metallic conductors. That's why copper is found in your electrical wiring, but not silver, because silver is too expensive. Okay, let's take a look at the next page. Is on density, another physical property. Okay. So density, generally density, right, transition elements, they have higher density than S-block elements. And how do we explain this? Very simple. If you know that density is equals to mass over volume. So for transition elements, right, generally the metal structure is more closely packed. If it is more closely packed, we can say that the volume is actually lower, right? Similarly, the transition elements, ions, okay, they have smaller atomic radii. In this case, volume also smaller. Because you know, spherical shape, right? 4 over 3 pi r cubed. So radius smaller, volume also smaller. So density will be higher, correct? This is very easy. Another trend for density that you need to know is that there is a gradual increase from chromium to copper. So generally this part is a gradual increase. Okay, why is that so? Okay, if you again refer to your density is equals to mass over volume, your atomic mass, okay, atomic mass increase, so your mass should increase. Your volume, okay, the atomic size is relatively constant. So volume below is actually relatively constant. So overall, there should be an increase, but it's a gradual increase, okay? Okay, let's move on to the next physical property, which is on atomic and ionic radius. Again, now, right, I would like you to do a quick comparison between the transition elements and the other period 3 elements. Okay, so let's take a look. If you look at the periodic table, right, from titanium to copper, this is our transition element. Okay, of course, scandium and zinc not in the transition element. They are relatively constant. This part, can you just highlight or circle the y-axis? This y-axis is for atomic radius. Okay, in periodicity you will learn more about ionic radius. Okay, for period 3, that means from sodium, magnesium all the way to chlorine, the atomic radius actually decreases. So the trend is quite obvious. Okay, so you also need to know how to explain all this. So can we turn to the next page, right? It is on a comparison table. This table is actually very easy to interpret. Let's go through it together. But before we move on, right, there is actually a small box at the top which I will need you to pay attention. This part we also learned in atomic structure before. Remember this part? Key points in explaining atomic radius. Okay, and also, okay, ionization energy, next one you will see. So we have our nuclear charge, shielding effect, and effective nuclear charge. So generally, our effective nuclear charge is our nuclear charge minus away the shielding effect. Okay, so in this case, right, let's see how we can explain these two trends. Okay, can you take a look at the table? Okay, so for the first column, we have atomic radius of period 3 elements. Just now we saw that they actually decrease across the block. Okay, for first row transition elements, we know that they are relatively constant or invariant. This part, can everybody please wake up and also write this part, because this part is actually not scandium to zinc, it should be titanium to copper for transition elements. So how do we explain this part, right? Let's look at period 3 first. Okay, it's actually very simple. You just need to use this equation to guide you in your explanation. So let's see. First point, we use nuclear charge. So across period 3, nuclear charge increase because there are more and more protons. Similarly, across the first row transition elements, nuclear charge also increase because more and more protons. Okay, for the next point, then we have to talk about shielding effect already. Okay, so for shielding effect, let's look at period 3 first. Okay, electrons, they are added to the same outermost shell. Okay, so the shielding effect will remain relatively constant. Okay, so let's see, now you can actually take this down. Effective nuclear charge is equals to nuclear charge minus shielding effect. So if your nuclear charge actually increases, but your shielding effect remains relatively constant. So you can actually, based on like mathematics, your effective nuclear charge should increase. Okay? So very easy to remember. Let's take a look at the other one. For first row transition elements, okay, let's see. This is the electronic configuration. If you notice, right, electrons, please take a look at point number B. Electrons, after being added into the 4s subshell, all the other electrons, right, will be added into the inner 3D subshell, which is all this. Inner 3D subshell will continue to fill until... So this inner 3D subshell, right, they actually shield the 4s electrons from the increasing nuclear charge. Okay? More effectively than the 4s electrons can shield each other, because the 4s electrons are on the same outermost shell. So 4s electrons cannot shield 4s electrons so well, but 3D electrons can shield the 4s electrons, okay, because they are in the inner parts. Okay. So in this case, right, if you take a look at, go back to the period 3 elements, right, just now we already show you that the effective nuclear charge increases. Okay, whereas for the transition elements, okay, for the transition elements, you can also take this down just to help you understand and also remember the points more easily. So if you notice, right, nuclear charge for the first row transition elements increases, but the shielding effect, right, is actually increasing shielding effect because there is a lot of 3D electrons that can shield the outermost. So you can actually, you know, put like, let's say 2 increases here to show that it increases much more than the nuclear charge. So in this case, effective nuclear charge should gradually increase. This part, please take note. Gradually increase. The key difference is for period 3 elements, right, it is like a very distinct increase, but for transition elements, it is gradually increased because the shielding effect also increases at the same time. Okay, so because of this, the valence shell electrons are attracted more strongly to the nucleus, so there is a decrease in the atomic radius. Whereas for the first row transition elements, because the increase in effective nuclear charge is very gradual, so the atomic radius of the transition element is like relatively constant. Okay, everybody? So take note. Okay, now the next point to take note of is comparison, because now what we have seen, right, is period 3 elements on its own, transition elements on its own. So now let's take a look at comparison, which is your third column. Okay, your third column. So third column is actually a comparison between your transition elements and the S block. So if you look at your third column, right, there's a top part and the bottom part. Top part is the generic template lah, but of course we want to move into the specific example, which is atomic radius of titanium versus calcium. Why is titanium smaller? If you take a look at the electronic configuration, okay, you notice again that when we explain in terms of effective nuclear charge equals to nuclear charge minus shielding effect. So again, we look at nuclear charge first. Because it's comparison, right? So we must say that titanium has higher nuclear charge because there are more protons, right? 22 versus 20. Because more protons. Then after that, we move to the next point, shielding effect. So we must say that titanium has more electrons. But in this case, the 3D electrons, right? If you notice, you can circle this part. 3D electrons as compared to the 3s2 and 3p6 actually provides poorer shielding effect. Okay, so 3d2 as compared to 3s2 and 3p6, they provide poorer shielding effect because of the shape of the orbitals. D orbitals, right, some of them look like this, like a flower like that. So they are like more diffuse, so they don't provide so much shielding. So in this case, right, if you notice this equation again, you can quickly jot down nuclear charge actually is higher for titanium, but shielding effect is actually lower. Okay, so effective nuclear charge should be higher also. So in this case, titanium has higher effective nuclear charge, and hence the 4s electrons, which is the outermost electrons, will be attracted more strongly to the nucleus. So titanium will have a smaller atomic radius. So in explaining, right, you just need to remember to have your three key points: nuclear charge, shielding effect, and effective nuclear charge. Okay, 10. Let's move on to the next page. Another physical property is our ionization energy. Okay, for ionization energy, right, all of you need to know how to explain the first and second IE. Okay, if you take note of the axis, this part is ionization energy, and they have plotted for the first, second, third, and fourth IE. Okay, please wake up if you're sleeping. Okay, this part, right, if you notice, the first and IE increases only slightly. So in this case, right, if you notice the graph, the first and second IE generally increases only slightly, whereas for the third IE, what do we mean by D subshell pattern? KIV first, later we'll go through. Okay, D subshell pattern refers to this part. If you see that there is like a bit of an anomaly, like suddenly there's a dip over here, that is what we mean by D subshell pattern. So how do we explain all this, right? How do we explain first and second IE increases only slightly? Again, if you notice now, we still make use of the 3 points: nuclear charge, shielding effect, effective nuclear charge, same as atomic radius. So for the first and second IE, the 4s electrons are generally removed because we know that we remove the 4s electrons first. So the first thing, of course, the points are not arranged so in order, but you notice I talked about shielding effect. So the 3D electrons actually shield the 4s electrons from the nucleus. But you know that the nuclear charge increases across the D block. Okay? And just now we know that the 3D electrons, right, they provide good shielding effect for the 4s electrons. Please take note, as compared to 3s and 3p, it is poor shielding effect. But when we are looking at transition metals alone, it's good enough. Good shielding effect. So in this case, the 4s electrons experience only a small attraction. So the increase in effective nuclear charge from element to element is minimal. So how do we write out, right? If you can, effective nuclear charge is equals to nuclear charge minus shielding effect. Okay, so we know nuclear charge increases, okay, but shielding effect is actually increasing. Shielding effect is increasing because the 3D electrons provide poorer shielding for the 4s electron. So generally, effective nuclear charge increases gradually. You notice this is the same as your previous table, column 2. It's exactly the same. Okay, so first and second IE also increases slightly, just like atomic radius increases slightly. Okay. Let's move on to the third and fourth IE. For the third and fourth IE, right, because after we remove the 4s electrons, the other IE will be to remove the inner shell, which is the 3D already. Okay? So in this case, the remaining 3D electrons provide poor shielding for each other. What do we mean? Just now we already went through, right? If the electrons you are going to remove are from the same subshell, let's say 3D, I want to remove, because 4s already removed, I'm now left with 3D. And I still want to remove 3D, they provide poor shielding for each other because they are at the same outermost shell. Okay? So in this case, there is a significant increase in the effective nuclear charge. So the electrons will be attracted more strongly to the nucleus. Okay? So generally it is, you can see a gradual increase. So this part again you can take down, effective nuclear charge equals to nuclear charge minus shielding effect. Okay, the nuclear charge generally increases, okay, but the shielding effect is actually poor. So overall effective nuclear charge will increase. So the electrons attracted more strongly, so the ionization energy is higher. Okay, let's move to the next stage. Okay, for the next stage, right, just now we were talking about the D subshell pattern, right? Now we are going to elaborate about it. Elaborate on it, okay? What do we mean by that? Okay, so D subshell pattern for the third IE, okay? You can actually highlight this part, third IE. Okay, so from the third IE, of course, we are removing the third electron, right? That is why we are considering Fe3 plus and Mn3 plus. Okay, Fe and Mn is the point at which your graph dip, okay, in the graph. So from the Fe2 plus to Fe3 plus, you notice that in the electron in box diagram, I have a paired electron. So this paired electron will experience inter-electronic repulsion. So it is easier to remove, require less energy to remove. Okay, that's why in your graph just now you see a dip. The drop just now, okay, is due to the Fe3 plus. Okay, whereas for manganese 3 plus, Mn3 plus, right? If you remove, it is just like a normal removal, just a single electron on its own. So that's why the third IE is higher than the Fe3 plus, okay? Okay, now we just have a little bit of time left. Can you try checkpoint 4 very fast and see what's the answer that you get? What's checkpoint 4? They're asking you to compare copper and calcium. So which property is the data under the correct element? A, B, or C, or D? Everybody, can you shout your answer? A, correct. I think this one very easy, yeah? A, yeah. Okay, so density, transition element definitely should be higher than calcium. Okay, melting point definitely should be higher, so this one is wrong. Electrical conductivity should be also higher, so this is wrong. Metallic radius, we know that is smaller, so this is wrong also. Okay, we have still a bit of time left. We will just go through quickly the summary at the back. Okay, very quickly. This summary, right, if you notice this table, if you look at the heading carefully, it is transition elements versus the other S block, such as calcium, example only. So generally for transition element, they are better electrical conductors, okay, and they are higher in melting point and boiling point, okay, because in this case, right, there are stronger metallic bonding due to both the 4s and the 3d electrons being able to delocalize into the metallic lattice structure. Okay, there are 3d and 4s electrons, both can be delocalized. Okay, yeah. So for part B, sorry, not this. Yeah, and then there is one more point in your chem bonding lecture notes, right? Don't forget, is the part about higher charge density. Okay, this part you can actually quickly jot down. This is on charge density. Okay, and then after that, on atomic radius. Atomic radius, generally transition element is smaller because we know that there is an increase in effective nuclear charge. Okay? Due to the poor shielding effect, please take note, poor shielding effect provided by the 3d electrons as compared to the 3s electrons and 3p electrons. Okay? Then the next part is density. Density, just now we saw already. The structures are generally more closely packed and they have smaller metallic radius. So density is equal to mass over volume. So volume drop, density should increase. And finally, the last part, lower first IE. Okay, lower first IE is due to your 4s electrons being shielded by the inner 3d subshell. Okay, as compared to calcium, or generally S block elements. Okay, so for this lecture, we are generally recapping what we did in atomic structure and chem bonding actually. Okay, so please go back and revise, because from next week onwards, right, you look at the next page, is chemical properties. Okay, for chemical properties, right, it is a lot of recap on your electrochem. Okay, chemical properties is a lot of electrochem and chem equilibrium. Okay, Ken? So this will be the second last topic. The last topic is periodic table.